Okay, so what we want to do in this first type of calculation is determine how much energy is either being absorbed or released from the surroundings in our various experiments. So again, just to go over the variables, Q is going to be the quantity of heat that is either released or absorbed, and that heat is going to be calculated by measuring the temperature change of the material. So what is it at the beginning? What is it at the end? And calculating this change in temperature. And we'll do that in degrees Celsius. Then we're going to have the mass of the material, and we'll use mass in grams. And then we're going to use this other number called the specific heat capacity. And its units are combined units. It's joules per gram degree Celsius. So if you remember from the last video, it tells us how many joules do we need to warm 1 gram up by 1 degree Celsius. And that information we can always get from a table. So we've got this table here where we can look at water. It says it's 4.18 joules per gram degree Celsius. So to warm up 1 gram of water by 1 degree takes 4.18 joules of energy. Okay? So that's what the C is. And in most of our experiments, C is going to be water or something very like water. But occasionally we may need to look up a different C value depending on what the material is, the mass that we're using in our experiment. Right? So again, when we calculate Q, we're going to need to know the mass of the material. And in our case, we're going to do that in grams. The change in temperature. And again, we'll just do that in degrees Celsius. And then the specific heat capacity for whatever the material is that we're warming up or cooling down. So let's take a look at a question where we do something fairly straightforward. We're going to take some solid sodium hydroxide. We're going to put it in water, so H2O, and we're going to have it dissolve. And when sodium hydroxide is put into water, it'll dissolve and form 2 ions, the sodium ion and the hydroxide ion. And when that happens, there is a certain amount of heat either absorbed or released in the water that this is happening in. So that's what we want to try and find out at this point. When I mix sodium hydroxide together, does the water that I'm mixing it in, the surroundings, does it get cooler or does it get warmer? So we're going to set up an experiment here where we have a mass of NaOH. I'm going to take about 7 grams of NaOH. I'm going to take about 100 grams of water. And then we're going to mix the two things together to see what the temperature change is. So we'll measure the temperature of the water at the beginning of the experiment, and we'll measure the temperature change, temperature final of the water at the end of the experiment. So temperature 2 will be the warmest or coolest temperature that the water ends up at. Okay, so let's set up that experiment and see what the results are. So we'll set up this simulation to see what happens when we mix the sodium hydroxide into water. So the first thing we'll do is we'll go to solids here, and we'll change our solid to sodium hydroxide. I'd indicated we were going to use 7 grams. In the other beaker, we'll choose a liquid. In this case, we're going to use water, and we're going to use 100 grams of water. And it shows that the water temperature and the sodium hydroxide are both starting out at 20 degrees Celsius. So there's our initial temperature, 20 degrees. And then we'll run the experiment. So to run the experiment, I'm going to put a graph up and a microscopic view of what's going on. And I'm going to hit start. And so when the sodium hydroxide is transferred into the calorimeter and stirred up, as the sodium hydroxide dissolves, you'll see the ions in a microscopic view start to spread out and move into the water. And you also should be noticing a fairly significant temperature increase. So it appears that our water is absorbing energy and getting hotter. Okay, and there's the end of the experiment. We can see the temperature went up to a maximum and then stopped at 37.40 degrees Celsius. So those are our two temperatures, 20 to start and 37.4 to finish. So let's go back to the other screen and take a look at how we do this calculation. Okay, so our initial temperature was 20. 0.0 degrees Celsius. Our final temperature was 37.4 degrees Celsius. And we know that the mass of sodium hydroxide was 7 grams, and that the water that changed temperature had a mass of 100 grams. So to figure out how much energy went into the water, we can simply use our Q formula. So we say Q, or quantity of heat, is equal to mass times the specific heat capacity times the change in temperature, which is equal to the mass times the specific heat capacity, and then we can write in here TF, or T2, minus T1, or TI, right? Put our numbers in. So that's 100 grams times a specific heat capacity for water is always the same. It's 4.18 joules per gram degree Celsius. And TF, T2 would have been 37.4 degrees Celsius minus the initial temperature of 20 degrees Celsius. And that will give us what we need in order to be able to calculate the amount of heat. Okay, so let's just grab a calculator and do the calculation here. So we're going to do 100 times 4.18 times brackets 37.4 minus 20. Close the bracket, so that's 17.4, and then that equals 7273.2. So let's add that into our calculation. 7273.2 kilojoule, or just joules, of energy were released and absorbed by the water. So that's, we know it's absorbed because this is a positive value. So the water absorbed, let's switch that over to kilojoules. We just divide by 1,000. So 7.3 kilojoules of energy was absorbed by the water when 7 grams of NaOH was dissolved. Right? So that's the first part of these questions, is using the data from what changed to calculate the amount of energy that must have been absorbed, in this case by the water, in order to figure out the energy change. Now, we can take that another step, because what we can do is the changes in the energy surroundings, so the water got warmer because the chemical system lost some energy. So we had two things going on. The system was the NaOH dissolving, and the surroundings was the water it was happening in. And so when we try and change that Q value, we can change it to another value called the enthalpy. And the symbol for enthalpy is delta H. So delta H, or enthalpy change, is going to be what happened to the atoms and molecules involved in the chemical change, and how did their energy change? Well, if we assume that what causes the surroundings to warm up was whatever the chemical change that was happening, then the energy that warmed up the water came from the chemical change. So we can write this. We can say that the change in energy, or the enthalpy change for the reaction, that's the NaOH dissolving, the energy involved with that is equal to whatever the value of the water's energy that it absorbed was, but change its sign. So what we're saying is enthalpy, if the Q gained energy and was positive, then the enthalpy for that reaction has to be negative, indicating that those chemicals, the NaOH, lost some energy. So we can quickly make a switch from Q, quantity of heat absorbed by the calorimeter, right here, to delta H, quantity of energy that was released by the chemical reaction, simply by setting the two equal to each other but changing the sign. Okay? Now, if we take a look at this reaction where we had NaOH going to form Na plus and OH minus, the calculation we just completed, then the enthalpy of dissolution, so what we would call this, and I've got the number wrong here, the enthalpy of dissolution, so how much energy was given off when we dissolve something, well, it would be equal to delta H equal to minus Q, and we just found out that Q was equal to, let me just grab a pen here again, sorry, was equal to 7.3 kilojoules, and that was not for 1.5 grams, sorry. We ended up using 7 grams in our experiment. So for every 7 grams of NaOH, we can expect that chemical reaction to release, so the negative now means delta H is a negative, release or lose 7.3 kilojoules worth of energy. Okay? It's kind of an odd unit, so we wouldn't probably use the unit kilojoules per 7 grams. We would convert that, and so we could change that into kilojoules per gram, or even better would be kilojoules per mole. So why don't we just take a quick look at how we do that. So if you go back and you can remember some of your conversion factors from grade 11. Right now we have a unit in kilojoules per 7 grams. We'd like to get delta H, but we'd like it to be in, let's do the first one. Let's do kilojoules per gram. So right now we have 7.3, negative 7.3 kilojoules per 7 grams. Well, if we want to fix that, all we really need to do is divide this through. We don't have to add any new units or anything. So we just need to do 7.3 divided by 7. So let's go back to our calculator again. So it would be negative, clear, negative 7.3 divided by 7. And then we get a new number, and we'll just call that 1.0 kilojoules per gram. Okay? So that's a little better. Now we can know if we get a gram of something, we know how much energy, sorry, this should still be negative. We know how much energy it's going to give up. Okay? Now we could change this a little bit more, and sometimes more useful would be to do it in moles. So if we wanted to get the same number in kilojoules per mole, we'd have to do the same thing. So we'd say that delta H equals negative 7.3 kilojoules. So that's something that we want. But we got to get rid of this grams on the bottom per 7 grams. So we multiply that by a conversion factor. We'd like to get rid of grams, so we'll put that on the top. And we'd like it to come out in moles. Okay? And so the grams, well, I don't know how many grams, but moles, if I use moles, I could set this equal to 1 mole, and that's equal to 40 grams. So the molar mass of NaOH is 40 grams per mole. So that's where the grams comes from, the mole. And then if we cancel out units here, like we do when we do conversion factors, grams will cancel grams. And then we can do a calculation here and come up with a number. So let me just grab the calculator again. Clear. So it's 7.3 negative divided by 7 equals that, times 40 equals that. So now we have negative 41.7. So negative 41.7 is the number of kilojoules of heat. Negative 41.7 kilojoules. If we took a whole mole of NaOH, that's how much heat would be released into the water. Right? So that's the enthalpy of dissolution per mole and the enthalpy of dissolution per gram. It's just converting the number that we got into something more useful, because it's very unorthodox and very clumsy to express your units in kilojoules per 7 grams or whatever the mass happened to be. So you'll always be asked to convert it to one of these two things, either kilojoules per gram or... Okay, I think we'll just leave this video there, and I posted some questions where you can use this Q formula and just get started into doing a little bit of enthalpy calculations. Most of the calculations on the first worksheet, though, just look at getting Q. And then we'll come back and we'll do a bit of an experiment. So I'm going to give you some data, and we're going to look at kind of energy that is involved in your food. So normally we call those calories, but calories are just the non-metric version of joules. So they're joules. We could also calculate how many joules of energy is in some food. So we're going to take a look at a calorimeter, grab some actual data, and we'll look at how to calculate the heat of combustion or the enthalpy of combustion. So when we burn a peanut, how much energy might come out of a peanut. And you could do this with any food. You could do it with marshmallows, Doritos, whatever you like. Just don't burn your house down if you're going to try this on your own at home. But we'll do one together using a video from YouTube, and we'll collect some data in the next video and run through another one of these calculations where we calculate out an enthalpy change. Okay, so that's it for now. Thanks.